Hey everybody, this is Larry. This is me going Q4, the weekly contest 251, delete duplicate folders in system. So this one was a very hard problem. As you can see, not that many people got it relatively. It took me about, what was it, 40 minutes plus a penalty to do it. But I think, to be honest, the idea is pretty like you probably have that idea, but you just didn't know how to implement it. I think the implementation was the trickiest part about this problem. Though there are a couple of ideas that you can think about. So yeah, so hit the like button, hit the subscribe button, join me on Discord, especially if you're into doing these contest problems, and we can go over them together right after the contest. So come to Discord, hang out with people who are who are nerds like me. But yeah, but for this one, so the short idea that you probably can gather is try to hash the tree, right? So how do you hash the tree? There are so many ways to do it. So um, I did it one way during my virtual contest, but I actually found a shorter way to do it later on based off this specific problem. And I think this is actually the fastest, or according to me testing, it was like 100% on time and space. So yeah. So basically, the idea for so my initial idea for this problem is just hashing it one at a time. And the key thing to know, and I'm gonna bring up Paintbrush real quick. So hang on a second. Okay. So basically, the idea here is that okay, we're adding nodes one at a time. First of all, the first thing I do, and let me see if this is on screen. The first thing I do, hang on, sorry, technical difficulty. Okay, you can kind of see it here. The first thing I do is sort by the length and then the X itself. And what does that do? That basically means that yeah, so basically that means that we do the top level paths first so that we add them sequentially and also in a lexicographic order, right? Meaning that we start the symbol string first. And the idea here for what I did was that first I begin with a node, right? Okay, that's a terrible circle. First I begin with a node, and I have some, there's some value to this node. Like for example, let's say this is A, and then I keep a separate hash for keeping track of its children or neighbors. I mean, its children or ancestors, right? This is an H. This is a terrible looking H, but okay, fine. Let me erase this real quick. Right. So basically, that's what I do. I keep track of let's say we'll put it. Oh man, the thing crashed somehow. Don't know why Paintbrush can crash. So sorry. Hang on. Let me bring it back. Okay, fine. Maybe I won't draw. But basically, for each node, you have I use the key. That's just called K, and then a hash that's just called hash, which contains all the child. And then now, let's say I add a child. What happens, right? I add a child. There's another circle, right? And then here, what I do is that I compute the before hash of the children. So here, for the child, there's also the key, which we return back, right? So after we calculate this, so in a recursive kind of way, after I calculate this thing's hash, which this thing's h to be more precise, I return a function that is based on these two variables back up. And then here, I adjust h based on the node that we added. That's basically the idea. And then the second thing that you might ask is, okay, well, what if I add another node, right? So in that case, what I do is that, okay, so there's this node, there's this k, there's this h. I update this h. Well, the h is going to be 0 in the beginning, but I update this key for k, and then I propagate it back up, change the color. I propagate it back up to change this H. And the thing to notice here is that when you change the H, what I did previously during the contest, and you can watch me solve it live afterwards, is that I took the previous hash value and then I subtract it, and then I add the new hash value in. So that's basically the idea. And then now, after this thing updates, what happens, right? Well, after this thing updates, I basically updates it, propagates it up again to update this H. So that's basically the idea. And there are different ways to hash it. I think I didn't even do a good job of this during the contest, during the virtual contest, and you could see it. But I play around with some ideas, and you don't really need a super good hashing on this one, as long as you have the ordering correct, which not everyone did, I think. Because if you do it naively, where you hash the entire subtree every time, it is going to be too slow. Though I think I did it in a weird way as well. I think you could have easily just construct the tree first and then hash everything and then propagate it back up that way. I think we could have done a better solution there. So that, because I think what I did actually is that I constructed a live version of it, even though it didn't need to be live. I think live-ish. I think now that I think about it, there's an easy way to implement this. But okay, now, but the other thing to notice is that actually, yeah. So basically, this H function is that if you have multiple children, then you just have to kind of, keep track of the children in a good way to propagate up to the same age. And as long as you do it consistently, it should be okay. The reason being that if you're doing them in the correct order for each node, for each, duplicate nodes, even though they're in a different place, if you do things in the same order, you would get the same hash code. And if you get the same hash code, then that's when you could see the duplicate, right? And there may be false positive, but there's no false negatives if you do them in the correct same order. That's, I think, the key that I have for this one. I'm gonna now go back to the code and kind of go over what I did, right? So now I have a node. I don't even think most of these are necessary, to be honest, but I kind of did them in a funky way when I did it. I think actually, let me make some minor adjustments, because I don't think that's necessary anymore. Because the cute thing is actually none of this is really that necessary anymore. But yeah, let's see. So this is the key thing, right? It allows us to add things in a deterministic way. And the key thing to know here is that when you add things, when you look at this example, for example, when you look at the A and the B, because you always add things in the X, Y, Z order, X, Y, Z, W, or for the B, then that's no good. And that's why I sorted it this way. And as long as you keep that invariant, you can actually just look at each children's hash and then just do some magic to it. Because as long as you keep on adding things in a good way, and actually that's what I end up doing to optimize it afterwards. Mostly because actually my original code was wrong, but it was wrong in a way that highlighted a property that I didn't notice, so that it was actually right, even though it was wrong, if that makes sense. And the key note is that, okay, for example, let's look at this example 4, right? If in this case, we know that for node A, we add X, and X we add Y, and Y we add Z or Z, right? And the same for B. Because we sort it in a way that adds them in the same order, the hash code for A or the subtree of A and the subtree of B will be the same no matter how you, because you do it in the same order. If you do it in the same order and all the nodes are the same, then you always get the same function. That kind of makes sense, right? If you don't do it in the same order, even though the nodes are the same, you may have a different function or some kind of weirdness. So that's basically the idea here, and you get away with a lot once you recognize that properly. So I'm gonna go over my code real quick, but I think that's the hard part, is the hashing the tree, is the implementation the wacky, because the other parts are just like, going through the depth first search and deleting duplicate hash codes, which we'll talk about in a sec. Okay, so my dubiously named thing. So here, for each path, I recursively create nodes as necessary and going to the children. And this is basically what I have here. I look at each path one at a time by doing recursive with a node, because I was trying to do it iteratively during the contest, but it kind of got weird. So yeah. So for each node, if it's not there, then I create a new node, and then I recursively do it, right? And once we are done with a node, I look at the hash value of that child, and then I add it to the current hash. And this is just, to be honest, you can actually substitute any other function here, as long as it doesn't give you too many false positives. It should be good. There should be no false negatives, but you just don't want false positives. That's basically the only thing that gives you tricky. And for each node, I actually have two things. As I said, there's a key thing, and then there's a hash thing. So hash is actually hash of all the children, not including this node, where key is just hash of this node's value, and then the get hash would be hash of all subtree, including this node. This part is a little bit more funky, and this way it allows us to do the duplicate checking while still considering the number and depending on your context. But yeah, so basically our recursive function will do one path at a time. It looks at each node, and it just basically does another hash on top of the delta, right? Because basically this current hash is a new addition. It's basically like a delta hash, if you want to call it that. It's just a hash on the change, not exactly it's not a hash of the children, it's a hash on the change. But because you do the same operation every time in a consistent order, because you sort it in this consistent way, this will allow us to build a hash function that should be consistent. Okay, so let's say you believe that. I know that you may have to play around to see why that's the case. I definitely advocate playing around to get that visualization. So yeah, so then let's say you believe that, then now collusion is made more straightforward. We basically do a depth first search looking for collusion. Here, we just look at the hash value, which does not, in this case, it does not include the, if you recall, it does not include this node. So basically, just look at the subtrees. I could rename this better, to be honest. That's my fault. Yeah, so we just look at all the subtree hashes, and then we recursively go to collide with the children, and then the go remove just mark things as something that they could be deleted if they're more than 2. That means that there's a collusion, so you do a deletion, and then the collect is just to get rid of all the node that is to be deleted. Yeah, and as you can see, everything is a depth first search-ish, recursive-ish thing, so it's going to be linear time in the size of the tree. Yeah. So yeah, and then space, it's mostly linear space, depending on how you want to count the characters. But because of the sum of the path, we don't really do anything more. Because for each node, keep in mind that we only store all of one space, and there's all of n nodes, I suppose, which is the size of the tree. So this is going to be all of n space, because we don't do anything more than that. I mean, this is, I guess, more, but this is also at most the number of nodes. So yeah. So all of n time, all of n space, and that's all I have for this problem. You can see me solve it live in the contest next. Okay, good. How are we doing? People already finished, is that right? Mistakes were made. Okay. Hmm. This is a weird problem. So you want to delete duplicates. Let's look at the constraints real quick. Oh, sorry. So the depth could be 500. This is one of those weird things. Semi-identical supplement. Okay, that's really weird. Well, that's going to be a hard one if even the good people haven't really finished it yet. Hmm. Hmm. Will be will it be given in order? Don't really have a good idea on this one. Hmm. I think it's just a lot of hashing, to be honest, on this one. I've been just thinking about ways to do this without a helper class, but maybe that's just the way to do it. Though 2 to the times 10 to the 4th, maybe a lot of elements though. We'll see. Hmm. How much time do I have left? So right now I'm just thinking about whether after we sort them, are we going to add them in a consistent order again? Um, This is such a weird problem. I mean, it's actually I don't know if I'm doing it correctly. I think the way that I'm doing it through is with Robin Cop, but implementation is a little bit yucky. Not sure I'm a fan of this, to be honest. This way. Maybe I should do this recursively because that's essentially what I'm doing. I don't even know if this is going to be fast enough. But and now we want to go recursively. It's just a random number, to be honest. I don't think this really makes sense. Mm-hmm. Let's just run the code to make sure that it runs without crapping out. Okay, and then now once that's done, I can do another recursion to see. Hmm. And then now, that spout is right. I feel like I'm doing that thing where collisions. Oh, this is some weird code. Let's want to see if it doesn't give me anything weird. Okay, so it runs. Whether it runs correctly is another story. All right, moment of truth. Oh, that did nothing. delete at the root level, huh? Oh, there may be a lot of zeros. Maybe that's why. Okay. What am I doing wrong here? Am I not doing this correctly? I never fixed the hash, have I? For leaf node. Leaf node is always 0. But we also want to make sure that we don't catch this Z case, right? I'm just being lazy. Does that work? Hmm. Hmm. Well, that did nothing. Zero. Oh, this is the root node. I am clearly not propagating this up correctly. E, A, B. Why does the A node doesn't have? Why doesn't the A node have this? So previous n index is the same in this case. I'm getting some weird errors. Is that I'm removing too much? No, the A and the C, okay. A and the C should be removed, but the D and the A should not. Why is the D and the A not? Is this right? I mean, it's kind of right, but it's not exactly right. Because this could be, because this is not factored into the current hash yet. Yeah, okay. I think that's where I'm wrong. There might be other things as well. Okay. This is a hard problem, as you can see. Still don't know what I'm doing. But why? Why does this collide on a D? Did I remove the root node by accident? No, it's everywhere, so seems like the root node's okay. And why does it collide? Why do you collide? I don't even know what the expected answer is. It seems like this is still wrong because it's missing CP and AB. Nope, AB is here. I don't know how to do this anymore. I mean, it's just a tough problem in general. How many people have gotten it so far? A lot of people have gotten it now, so we should get this one. I mean, I feel like this is the right idea. My implementation might be pretty bad, pretty poorly. Just doing a lot of debugging, seeing what I can do. Okay, so AB. So the root node is this thing, and then it goes to AB is 0. That's really weird. Well, that's really why, because AB is 0, and we don't. Leaf nodes are 0 for that reason. How do we get rid of leaf nodes? Oh, I guess if just we don't check on 0 because it doesn't have any. I guess that's fair. Okay. Maybe that's what I need to do. Ignore that hashes. Because I think I'm just handling leaf nodes that happens to collide on a D node. That still shouldn't happen though. Is this right? I don't even know what the right answer is. Alright, let's get rid of some print statements first. DTA, CPAB. It just doesn't seem right? Oh, actually, maybe it's right. CCPAAB. I might still get this wrong, but at least I think I'm a little bit better. Okay. I don't even know if this is the right answer because it's so hard to compare these things by inspection. But let's give it a go. Let's just give it a submit. We'll see what happens. Okay, wrong answer. That's fine because I did not want to spend too long on this to come up with test cases. But this is just really weird. Okay. Okay, so I'm really wrong on this one. C should not be removed. Why did I remove C? That's weird. Let's put this somewhere. I think those are just test cases, but okay. Also, I forgot to remove some debugging things, but in this case, I needed it back anyway. Okay. No, I want this here. There's still too many zeros. Maybe that's why. C has a 1. This is a really bad hash code, clearly. C has an A and a B and like it has a bunch of stuff, right? So that hash code should not be 1. So that's just really wrong. And that's probably why a lot of things got. And also these P's are 0. That's just really weird. What am I doing wrong? Why are my hash codes not working? Why? Oh, I think I'm messing up here. No, I think I'm okay. No, I don't think so. Because I think this is. Okay. So this at least gives me a lot Okay, so now at least it changes some stuff. But it doesn't give, the B is still 0, which is still wrong. Why? Why is B 0? Is this on the B node or the A node? That's what I'm trying to see. This is on the root node. Oh, because we're recursive. So this B node is giving me 0, so I've actually been reading this wrong. But okay. So on the B, maybe something like that, because it was just doing zeros, because I'm dumb. Okay, so this is way better, I think. What was the expected answer? Oh, CCA, okay. So let's go. I don't know how much time I have left, but it's fine. So I need to get rid of my print statements before they give me more of an issue. And I also want to get rid of this because it's just doing too much otherwise. All right, let's give it a spin. Does this look good? This one looks good. This one looks good. I think this looks good. Let's give it a submit. Come on, baby. Whew, that was a hard one, friends. Yeah, thanks everybody. Thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Hope y'all have a great weekend. Yeah, see you later. Stay good, stay cool. Bye bye.